Hi students, we are still in chapter 6 and we need to talk about something called chemical equilibrium. Now if we take a look at the first equation, we have hydrogen gas and iodine gas and they are reacting to form HI. And we see that we've got the regular old arrow that we're used to, and that indicates to us that we take all of our hydrogen gas and all of our iodine gas and it all gets made into a couple of HIs right here. But that's not always what happens. We don't always make 100% product. In most cases, we don't. So we have a couple of different types of arrows down here. And the first one looks like this. And that's indicating that that reaction is going both ways. And that looks kind of funky. But what we're saying is that we have hydrogen gas and iodine gas. And when they first meet, they react pretty quickly and make some HI. And then we get to a point where the reaction slows down and the H2s are having a hard time finding the I2s and making HIs. And then we get to a certain point where the hydrogen gas and the iodine gas, they're just done. They float around and they're like, oh, we just don't feel like doing it anymore. So we still have some of our reactant hanging around, as well as our product. So these three things are all in the same container together, just floating around, and we have constant concentrations of those things. And what we get is every once in a while an H2 will find an I2 and they'll react and make an HI. But at the same rate, what will happen is that a couple of HIs will find each other and the reaction will go backwards and will make an H2 and an I2. And if you have the same rate of forward reaction as reverse reaction, and you have constant concentrations of the different compounds that you have, you're at something called a chemical equilibrium. And that's why we have the double arrows there. That's indicating that the reaction has come to an equilibrium. Now, the other way you'll see the double arrows drawn is like this. It's a nice fancy double arrow system right there. And that just means the same thing. So again, to define equilibrium, we have a condition where the rate of the forward reaction is equal to the rate of the reverse reaction, which means that the concentrations of the reactants are staying stable, they're staying the same, and the concentration of the product or products is also staying the same. It doesn't mean that they're equal. It just means that they're constant. And if an H2 finds an I2 and they get together and produce a couple of HIs at the same rate, a couple of HIs will find each other and go backwards and make an H2 and an I2. So again, the concentrations of reactants and products are constant once we reached equilibrium, but it doesn't mean that they're equal. So the little ants down here are showing you that once we reach equilibrium, we have a certain concentration of reactants and we have a certain concentration of products. And if we make some products at the exact same rate, we're going to make those reactants in order to keep those concentrations constant. So if we look at the next slide, what we'll see is this exact same reaction, but we have some white and purple blobs here. So it's just a different way to visualize this. So at the very beginning of the reaction, at time equals 0, when we're right here, we don't have any product. We don't have any HI because H2 and I2 have not yet met. So right at time equals 0, you're putting these two things together, and your hydrogen gas and your iodine gas, they've got to collide with correct orientation and correct energy in order for the reaction to happen. And as the reaction goes along, you can see we're making HIs. So in picture B right here at 16 or 17 seconds, it's showing you that we've got 4 HI molecules. And then time goes on a little bit, and we're right here at 32, 33 seconds. And you can see that we've got 8 HI molecules here. And then we're right here at 46, 47 seconds. And if we count up our HIs again, we can see that we've got 8. Now, between 32 or 33 seconds and our 46 seconds, our concentration of HI stayed the same. So we had 8 HIs, oops, went off the page there, 8 HIs here, and 8 HIs here. So our concentration of our product stayed the same. We weren't going to make any more. And if you count up your hydrogens and your iodine molecules also, you'll see that those also remain constant. So right here, we've reached equilibrium. We have as much product as we're going to make. And the leftover reactant that we have there doesn't want to react anymore to make any more product. So we've got what we've got right there. But again, occasionally an H2 and an I2 will find each other and make a couple of 2 HIs. But at the exact same rate, what's going to happen? A couple of HIs are going to find each other, and the reaction will go backwards, and we'll form an H2 and an I2, keeping the concentrations of all of these guys the same. Okay, so keeping them constant. So moving on to the next slide, what we can look at here is the exact same reaction, but we're looking at a graphical representation of the reaction rate of the forward reaction versus the reverse reaction. And right here, we'll have time equals 0, and if we have a reaction rate of 0, it's down there too. Now notice at the very beginning of the reaction, up here, the reaction rate for the forward reaction is very high. It's a high number up there. And as the reaction progresses, as we react more and more H2 and I2 together, the reaction rate is going to come down. So we're going this way. The hydrogen gas and iodine gas are having a harder and harder time finding each other in order to collide. Now, at the very beginning of the reaction, you can see that the rate of the reverse reaction is down here at 0. Because at time equals 0, we don't have any product. At t equals 0, that's right at the moment where you're pouring the H2 and I2 together and they haven't reacted yet. So there's no HI to go in the reverse direction. So we have a reaction rate of 0. Now, as the reaction progresses and we're making more and more of our product, the product molecules have an easier time finding each other, and we can see that the rate of the reverse reaction starts to increase. There's going to be a certain point where the rate of the forward reaction equals the rate of the reverse reaction. and the concentrations of H2, I2, and HI are constant. And this, friends, is equilibrium. The rate of the forward reaction and the rate of the reverse reaction are equal, and the concentrations of H2, I2, and HI remain constant. And on the next slide, we have a different graph, and it looks extremely similar to the graph we just looked at, but instead of having our rate on our y-axis, we have concentration. So back here, we were looking at how the rate of the forward reaction decreases as the reaction progresses, and the rate of the reverse reaction increases until they reach an equal rate. So we've got equilibrium in here. So that's reaction and time. And on this graph, we're going to look at concentration. And we could also call this time down here. So reactants proceeding towards equilibrium. So at the very beginning of the reaction, when time equals 0, what we have is we have a very high concentration of our reactants. So we have concentration of H2 and concentration of I2. So remember, when you have brackets around something, the brackets in chemistry mean concentration. So brackets around H2 mean concentration of H2. So you can see how the concentrations at time equals 0 of your reactants are very high. And as the reaction progresses, the reactant concentrations decrease. And that makes sense because you're using them up. You're using up H2 and I2 to make a couple of HIs. So the concentrations of both of those things are coming down. At time equals 0, right here, the concentration of HI is 0 because at the very beginning of the reaction, you don't have any HI. So that should make sense also. As the reaction progresses, the concentration of your product increases, and that should make sense too, because why are you doing the reaction? To get product. So it makes sense that the concentration of the product increases. And we're going to get a decrease in the concentration of our reactants and an increase in concentration of our products until we reach a point where the concentration of the reactants is constant and the concentration of your products is constant. So if you have constant concentrations of reactants and products, this little zone in here is called what? Equilibrium. Okay, so right in here where we have constant concentrations of our reactants and products, we have equilibrium. And if we look at the slide before, that's that same zone in there where you have equal rates of the forward and reverse reactions. Okay, so how do we take this qualitative concept and make it quantitative? Meaning, how do we throw numbers in here and torture you with math problems, right? So this is how we do it. We do it with the equilibrium constant expression. So first of all, we're going to need to write out an equation, and then we're going to need to throw some numbers in there and do some math. Math! And our equilibrium constant, which is K, and it's a big K, and in this case it doesn't mean Kelvin, it means our equilibrium constant, is the quantification, or making it into a number, of relative concentrations of reactants and products at equilibrium. And what we're going to do is we're going to put the concentration of our products in the numerator and the concentration of our reactants in the denominator. But it's not quite that easy because you can see that we've got a bunch of exponents all over the place there, and the exponents are A, B, C, and D. But not only do we have A, B, C, and D, we have lowercase and we have capital A, B, C, and D. So what on earth is going on here? Well, the lowercase letters, those are coefficients. And the uppercase letters, those are your compounds. So A could be something like 2H2O. So the little a would be the coefficient and the big A would represent your compound there. So we're going to go ahead and we're going to put the concentration of our products, and we're going to raise it to the power of this little coefficient here. So that would be the concentration of C to the power of the coefficient there, and you guys can see that appears right there. We do the same with D, and then we put A and B in the denominator. And what on earth am I talking about? Don't worry, we'll practice this. But anyways, this is the beginning of how we turn this into numbers and how we make you scream, please no, right? Word problems. Ah! But first, let's practice how to write the expression before we give you guys some calculations. Now, looking at this, we can see that we have a couple of N2O5s, and they're going to react to make 4 NO2s and 1 oxygen molecule. So if you need it, you can go ahead and put the coefficient 1 there. So remember, on top, what you're going to have is your products. Now, most students, when they think about this, they want to put the reactants on the top and the products on the bottom because that makes sense to most of our brains. But it's the other way. It's products on the top and we have reactants on the bottom. Okay, so products first. What we have here is we have NO2 and we put concentration of NO2. And remember, brackets mean concentration. So if we slap the brackets around NO2, what we say is concentration of NO2, and then the coefficient is 4. So the concentration of NO2 gets raised to the 4th power. And then we multiply that by the concentration of the other product. And the other product is O2. So in the balanced equation, it says that you guys are adding these things together. But in the equilibrium constant expression, we're going to multiply them. Sorry, but that's the way it goes. Okay, so the concentration of O2, you don't see an exponent there. And when we don't see a number, we assume it's what? It's 1. So you guys can write that in there if you need it, just to show that the 1 is corresponding to the 1 up here. And now in the denominator, we want to put the concentration of the reactant or the reactants. And we did that. We put that right there. And the coefficient on N2O5 is 2, and so we raise the concentration of N2O5 to the 2nd power. So right here, this is the equilibrium constant expression for this reaction right here. So let's practice a few. Okay, so we have number 1, 1, and 1. I don't know what happened there, but we'll roll with it. Okay, so if we want to write the equilibrium constant expression, we want to remind ourselves that we have product or products, concentration of that, over the concentration of our reactants. So looking at this, our product or our products are what? HI. So we'd write that our equilibrium constant is equal to the concentration of HI. And what am I missing there? I'm missing raising this to the second power. And then on the bottom, I'm going to put the reactants. And I've got H2. And I raise that to what power? I raise that to the first. And you can see here that if you haven't balanced your equation correctly, it's going to mess up the math later. Because if you have the wrong numbers for concentrations, you're going to get the wrong K. And if you guys need to put the 1 there, okay, but you don't have to. And then what's next? You have to put the other reactant down here. So the concentration of I2 and the coefficient on that, if we wanted to slip it in right there, would be 1. And if you need to write the 1 up there, go ahead. But remember, when it's 1, you don't have to. Okay. The second number 1 right here, we have methanol. CH3OH is methanol. And we have that decomposing into carbon monoxide and hydrogen gas. So first of all, are you balanced there? You've got 1 carbon on each side, and you've got 1 oxygen on each side. And on this side, you've got 4 hydrogens, and on this side, you've only got 2 hydrogens. And on the product side, the hydrogens come in pairs. So how many H2s do I need for 4 hydrogens, 4 individual hydrogens? I need 2 of those. Okay, so good. We've balanced that, and that means that there's a higher chance that we'll write the equilibrium constant expression correctly. Okay, so K equals, and we got to remember we've got products on the top. Kind of backwards from what we would think. So we have carbon monoxide, and the coefficient there is 1, so you can write it up here, or you do not have to. And then we have the concentration of hydrogen gas raised to what power? 2, because the 2 is right there. And then we're going to divide that by the concentrations of our reactants. And we only have 1 reactant here, and that's methanol. So we have CH3OH, and we raise that to what power? To the first power, and we don't have to write that. Now CH3OH, the other way that you could write that formula is CH4O. But CH3OH, that's written in the condensed format because that gives us a clue to the structure of that molecule. So if we were to write out the Lewis structure for that, we would see that we've got a CH3 unit bonded to an oxygen, and then the oxygen's bonded to a hydrogen on the other side. So that's why it separates those 2 hydrogens from each other, because they are in different chemical situations there. Alrighty, so the third number 1, we've got nitrogen and a hydrogen gas reacting together to form some ammonia gas. So we've got 2 nitrogens on the reactant side, and we've only got 1 nitrogen on the product side. So how many ammonias, NH3s, do I need to get 2 individual nitrogens? I need 2 of those. Now, that means that now I have 6 hydrogens, because 2 times 3 is 6. And on the reactant side, the hydrogens, they come in pairs. So in order to get 6 individual hydrogens, how many hydrogen molecules, H2, do I need? I need 3, because 3 times 2 is 6. Okay. So that means that we had a nitrogen molecule, and we had 3 hydrogen molecules, and what they did was they formed 2 ammonia molecules. Just in case you needed a little Lewis dot structure refresher there. There you go. Okay, so back to writing the equilibrium constant expression. What we have here is we have our product, and that goes on the top. Our product is NH3. We raise that to what power? To the second. And then we have the nitrogen molecule raised to the first power, but we don't have to write the 1 there. And then we have, oops, not H3. Bad, teacher, bad. We have H2 raised to what power? Kind of gave it away there, huh? All right, to the third power there. So that's how we write the equilibrium constant expressions for our reactions. Now, why on earth would I do all of that? Why? This kind of seems a little crazy. Well, there's a meaning to the numerical value of K once we start putting numbers in there. And when you have a K that's greater than 1, it means that you have a product favored reaction, which means that your reaction will make a lot of product and there will only be a little bit of reactant left over at equilibrium. And if we look at K, we've got concentration of product over concentration of reactant. So if we have a really big K, a lot bigger than 1, it means that we've got a big number on the top and a little number on the bottom. So if the concentration of the product was 10, whatever unit it is, and the concentration of the reactant was 2, again, whatever unit, don't worry about that right now, we'll learn it in another chapter. What you would have is a K that's equal to 5. So you can see that if you have a K that's a lot greater than 1, it's telling you that this reaction is product favored. The reaction's going to make a lot of product. If you have a K that's less than 1, that's telling you that you're not making much product. So say you had, let's see, 2 over 10. So the concentration of your product is a lot less than the concentration of your reactant. What would your K value be there? So we get 0.2. So again, when K is greater than 1, we're product favored here. And on the next slide, we'll see that when K is less than 1 or a lot less than 1, we're reactant favored. So you guys can see that in this little example there. The concentration of your reactants was a lot bigger than your concentration of your product, and you got a number less than 1. Okay, so what kinds of reactions have a K that's greater than 1? Well, if we react hydrogen gas with bromine gas, it's going to give us a lot of HBRs. And how do I know that? Well, if I look up the K value for this reaction, I'll find that K for this reaction at 25 degrees Celsius is 1.9 times 10 to the 19th. That is a huge number. That means you take this decimal point and you move it over to the right 19 times. So there's a whole lot of zeros there. That number is way bigger than 1. So it's telling you lots of product from this reaction. Very little reactant left over. And what does that look like graphically? Well, what we have is a concentration of our product at equilibrium that is way above the concentration of our reactant at equilibrium. So if we take a look at this right here, this graph, we can imagine that it keeps going like that at the equilibrium. So if we were to write out the equilibrium constant expression for this reaction, we would see the 2 appearing up here, and our concentration of our hydrogen gas and our bromine gas would both have exponents of 1 because the coefficients in the balanced equations are 1. And right here it says large number. That is that number right there, not the 25 degrees Celsius, this number right here. And indeed, it is a very large. So that is a very product favored reaction. Okay, so when K is a lot less than 1, and again, remember that K is concentration of product over concentration of reactant. So when K is less than 1, it means that you've got a big number down here and you've got a small number up here. Because if you have a small number divided by a big number, like 2 divided by a billion, your K value will be small. It'll be a lot less than 1. When your K value is less than 1, you are reactant favored, meaning the reaction does not make much product. It shoots out a couple of product molecules, and then the reactant molecules get lazy and they're like, nope, we're not gonna do any more. Nope, we're not doing it. And an example of this is nitrogen gas and oxygen gas reacting to form a couple of no's right there. And having a K value that is a lot less than 1 tells you that this reaction does not make much product. The K value for this reaction is 4.1 times 10 to the negative 31. That is a tiny number. That means you take this decimal point and you move it to the left 31 times. So this reaction does not happen very often. And that is a good thing because the air that we breathe in is mostly nitrogen gas. It is about 80% nitrogen gas and about 20% oxygen gas. And I fudged those numbers a little bit because we got a little bit of argon in there, carbon dioxide, and most of us live in the Inland Empire, and so we've got all kinds of other nasty things in there. So I'm approximating a lot. And if we had a large K for this reaction, meaning this reaction was product favored, the nitrogen gas and the oxygen gas would find each other and happily react and form NO, which we don't want to breathe in because we need oxygen to live. So we're very happy that this reaction has a very small K because we like to breathe. So what this looks like graphically, at the very beginning of the reaction, you have this concentration of reactants, and what they do is they find each other a little bit, and then they're like, no, we don't want to. And so at the beginning of the reaction, you have no products, and then you make a little bit of product, and then the reactants give up. I wish the program would stop making a line there. Don't do that. So you make a little bit of product, and then the reactants are like, nope, no more. We're not doing it anymore. So you have a reactant-favored reaction. Your reactant concentration is a lot higher than your product concentration. And if we look at the equilibrium constant expression, this number on top is small, and the number on the bottom is large. So when you take a small number and divide it by a large number, like you take 2 and divide it by a billion, your answer is going to be a small number. It's going to look like 4.1 times 10 to the negative 31. Okay, so what happens when K is about 1? It's approximately 1. Well, whenever you have a numerator and a denominator that are the same, like 3 divided by 3, you get the answer 1. So if you get a concentration of product and a concentration of reactant that are about the same, you're going to get a K value that's about 1. So that means that neither direction is favored, products or reactants. So the reaction proceeds about halfway, and then everybody's like, okay, we're done. And if you want to figure out what the concentration of your reactant and your product is at equilibrium, you have to do some calculations. So if you weren't listening up until this point, you were just letting me blah, 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 blah while you text your date for Friday night. Here's a handy dandy little diagram for you guys. And we'll notice that when K is about 1, it says you have a moderate reaction. You get about equal concentrations there. And don't worry that this says K with a little c subscript on it. The little c just means concentration. It's not a big deal. You'll see that sometimes. Sometimes you'll see EQ down there for equilibrium. Okay. Large KC right here, that means that we've got a lot of products being made. So it's a product favored reaction. And a small k means that we are reactant favored reaction. Okay, so when we reach equilibrium, we have a lot of reactants sitting around and not very much product. Okay, so here's another table for you guys. And what you'll notice is where you have equilibrium constants that are greater than 1, you're going to be product favored. And the ones that are less than 1, they are reactant favored. Exactly what we just talked about. Now we have come to the calculations, but we really only have one that's a big calculation. We got one that looks really scary, number 1. So we've got cadmium, and we have some NH3s that are hooked up to that cadmium. And not only that, but it's a +2. And not only that, you're dissolving it in water. So that thing looks really crazy. And then it separates into a cadmium cation and 4 ammonia molecules. Strange. You don't know how to do that, right? You're going to run screaming away from my video? No, you're not, because the question says, is the following reaction reactant favored or product favored? It doesn't ask you to do anything else with it. And so if we want to know if something is reactant favored or product favored, what we would do is look up the K. But you don't even have to look it up because I've put it right there for you. Now, is K less than 1, about equal to 1, or greater than 1? Well, the exponent right here is a -7, so that would mean you'd be moving this decimal over 7 spots. I don't know why it just made another line. It's liking to do that today. Bad program, bad. Okay, so what we have is K is a lot less than 1. So we have a reactant favored reaction. That means that in solution, we've got a lot of this stuff sitting around, and we only have a little bit of this. Because remember, K is the concentration of product over the concentration of reactant. And if you have just a little bit of product, so you have a small number up here, and you've got a lot of reactants sitting around, that's a big number down there. And that's going to give us a small K value, which we have. It's a lot less than 1. So we have a reactant favored reaction here. Okay, so that means we've got lots of reactants sitting around and it doesn't make much product. Now, number 2 says a reaction mixture that originally contains 11 moles of A and 0 moles of B in a 1 liter container is allowed to reach equilibrium. And we want to know what are the concentrations of A and B at equilibrium. Okay, so if we look at this reaction and our K value, it looks like we're missing some information. We can see that K is equal to 10, so that means it's probably reactant favored or product favored, you guys. Well, it's a lot greater than 1, so it's product favored. Now, what are the concentrations of A and B at equilibrium? Well, if I write K out a different way, if I say K is equal to the concentration of product over the concentration of reactant, you guys can see that we've got a numerator and a denominator. Now, sometimes when we just have a whole number, we forget that there is a denominator there. So what's the denominator on 10? It's 1. Does that make sense, you guys? 10 divided by 1 is just 10, right? Okay. So K is the number at equilibrium. So what we have is we have the concentration of the product at equilibrium divided by the concentration of reactant at equilibrium. So what we have is the concentration of product at equilibrium is 10, and the concentration of reactant at equilibrium is 1. And if I draw it out in picture format, so I've got 11 A's there. And those 11 A's are going to proceed to B's except for one of our A's. So we have 11 A's there, and it says we originally had 11 moles of A. So if you think of that as like 11 molecules of A or 11 A's, and we don't have any B's at the beginning of the reaction, but we let the reaction go, what we're going to get is we're going to get 10 B's, and we'll have 1 A, and the concentration of B's at equilibrium, that's the product, goes on the top, and the concentration of reactant at equilibrium goes on the bottom. So we have a product concentration of 10 and a reactant concentration of 1 at equilibrium. Again, you guys don't worry too much about the units on this stuff. We will get to molarity when we do the solutions chapter, and also the units on K can be a little bit funky. And if you guys go on to take general chemistry, which is Chem 1A and 1B at RCC, you'll do a lot of work with the units of K. And a lot of work with K in general. 1B is all K. Ka, Kb, Kc, Keq, Kw, Ksp, la 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 la, lots of K. All right, so moving on to our last problem here, phosgene. This is a toxic substance that's produced by the reaction of carbon monoxide and chlorine. The K for the reaction is 5. If the equilibrium concentrations for the reaction are 0.25 and the big M is molarity, but we say 0.25 molar, that's just how we say it. And the concentration of COCl2 is 0.8 molar. What is the equilibrium constant of carbon monoxide? Whoo! Okay, math problem coming your way. But first of all, let's go ahead and remind ourselves that K is equal to the concentration of our product or products divided by the concentration of our reactants. And if we want to specifically put the products and the reactants into this equation, we want to first make sure that our equation is balanced because we need to use the coefficients. So let's go ahead and do that. So we've got 1 carbon on each side, we've got 1 oxygen on each side, and we've got 2 chlorines on each side. So yay, it's already balanced. If you guys need to write the ones in there, go right ahead. So we have the products on the top. So we have COCl2. And we have the concentration of our reactants on the bottom. If you guys need to write the exponents in, go right ahead, but you don't need to because they're 1. If they're any other number than 1, you'd have to write it there. And where did I get those ones from? Right here on the balanced equation. Okay, so what we have is that K is equal to 5. So we're solving for the concentration of carbon monoxide because the question gives us the concentration of Cl2 and of COCl2. So we need to do a little bit of magic of algebra and we need to plug and chug. So if I go ahead and replace this with K for just a moment so I can do the magic of algebra, and then I'll put the 5 back in there. What we'll do is we're going to move K down here because things can move diagonally across the equal sign, and take CO and move it up here. What we're going to get is the concentration of COCl2 divided by K times the concentration of Cl2 of chlorine gas is going to equal the concentration of carbon monoxide. Now, if you guys want to do that the old algebraic way where you have to divide both sides by K and multiply both sides by concentration of CO, be my guest. That's fine to work it like that. And most of us want a variable that we're solving for to be on the left-hand side, so you guys can just switch that around if you need to. If you don't need to, fine with me. But some people need to do this. Okay, so now we're going to do plug and chug. So the concentration of carbon monoxide is the concentration of COCl2 on top. So you have 0.80, and I purposely didn't write in molar there. Again, you guys, I hardly ever say ignore the units, but for K, because it is a little bit funky, we can kind of fudge it here and just ignore it because K has a little bit weird units that I don't want to get into. When you get to 1A, you will definitely use that. Okay, so then we have 5 on the bottom because K is 5. And then we are going to multiply that by the concentration of chlorine gas, which is 0.25. And if you pull out your calculator and you do 0.8 divided by 5 and hit the equals, and then do divided by 0.25 and hit equals again, what we will get is 0.64. And it's a concentration, and the unit of concentration that we're using is molarity. Again, don't worry about where the molarity unit comes from with this one. You'll learn the weird units of K if you go on to general chemistry. Okay, so that's a concentration, and it has a concentration unit on it, which is what we want. Yay! So the next slide goes into Le Chatelier's principle, and that will be on the next video. Phew, I'm done. All right, see you next time, you guys. Bye-bye.